we talked about experiment. We also introduced the idea of the difference in difference estimators. So basically, just to go through what we learned, we define a randomized control experiment. The idea is that the treatment is, we make the treatment uncorrelated to the residuals. And if the design of the experiment is good enough, then we are actually able to get unbiased and consistent estimators for the causal effect, which is defined as the difference in the conditional means of the outcome variable when the treatment is equal to 1. So for the case in which we are in the treatment group minus the conditional mean of the outcome variable where we are in the case of the control group. Okay. So whenever this is the case, then we estimate by the average treatment effect, of course, because we cannot estimate the individual causal effect, and we do that by using the difference estimator. Okay. Okay. So then we talked about the threats to internal validity and external validity for this kind of experiments. So now we will go briefly to the quasi-experiments, which we already introduced last time. And the idea is that they have a source, also called the natural experiment. They have a source of randomization that is as if randomly assigned. So this is not an experiment. We are not in a lab, but there are conditions as if the treatment that we are evaluating is randomly assigned. Okay, so let's think of an example. This could be a new policy measure, an increase in the tax rate, in the marginal tax rate in two states where, and we compare the treatment group, which will be the state where there has been this increase in the tax rate, to a state where this increase is not there. Okay, so this is an example of quasi-experiment. And we will see, so here there should be, okay, RD is fine. Otherwise we call, so we do today the difference in difference estimator, and next time the regression discontinuity design. So you will find DID for the difference in difference, and RD or RDD for the regression discontinuity design, okay? So if, thanks. If an experiment, a quasi-experiment is conditional on observed variables, okay, so if there are other characteristics, other variables which may affect our outcome variable, we so the idea is that in a quasi-experiment is more difficult to actually clean for these sources of endogeneity because we are not in an experiment. We are not in a randomized control experiment. So it's more possible that there are other variables that we need to add to our equation as controls. And if these are observed, so just include this variable and you can estimate the treatment effect by ULS. Otherwise, if this is an unobserved variable, then we need to use the difference. In the first case, this is of course the model that we need to consider, and then the conditional independence assumption has to be old. So the treatment has to be uncorrelated to given one W. We have done this many times. I'm not going through this again. So whenever this W is unobserved, we have and if we can also assume that this W is time invariant. Okay, so this should be unobserved and time invariant. So whenever we have two periods, this W is constant over these two periods. Then we can use this difference in difference estimator, which is, as the name tells, not only a difference between the treatment and the control group, as we've seen for the experiments, but this is also a difference over time. So in the two periods that we consider. So we control both for differences between groups and for differences over time. So before and after the treatment. Why do we do that? So because there could be differences in the control and treatment group already before the treatment. So this is something that doesn't happen when we are in an experiment, because the treatment is randomly assigned. So there are no other characteristics which may affect the pre-treatment outcome variable. Here there is a variable W which affects this outcome variable Y before the treatment, which explains this difference in Y before the treatment. So even if, so in the end we will be there, we will be here, okay? So in the end we will run a regression model which takes into account change instead of levels, but changes in the outcome variable, and we don't have the data. So we are actually able to run a regression to estimate this causal effect here, which is the effect of the treatment. This is something that we want, without actually using data for W. So this is where we will go. But basically, the idea is that there is a W variable which affects, which explains this difference before the treatment in the control and in the treatment group. So we will make an example. And this is something that we want to clean, okay, from our estimation, because we want just to estimate the effect of the treatment on Y when they have the same start initial value, okay? So if we did not account for this difference in the initial values, we will basically estimate this effect, okay? So the difference, as I told you before, the difference estimator is the difference in the sample mean, okay? So the estimator for the, of course, for this causal effect would be the difference between this value and this value. So this would be the difference estimator. But as you can see, this measures the average treatment effect, okay, on Y. But if there are if the starting values are different, then by estimating this effect, we will basically also embody these different initial values. But we want to clean for this. We want just to see the effect of the treatment on Y. And to do that, we use these differences in difference. So we first compare the before and after the change variable sample mean for the treatment group. So this is the treated group, okay? This is the control group. Okay, so we compare what happens after to what happens before, what was before the treatment. This is the effect of the treatment in one group. This is the treatment group. And then we compare this to what happens over time with respect to the control group. So here there should be a delta, okay? And this is the change in the sample mean in the treated group over time, over these two periods, minus the change in the control group in these two periods. So as I told you, if we just estimated the difference between what happened at the end of this experiment, quasi-experiment, as we do for the experiments, we would overestimate the treatment effect. Why? Because we have this, because the initial value for the treatment group was already higher than the control group before the treatment, before the quasi-experiment. So if I want, for example, to measure the effect of one policy measure on some individuals, if those individuals, for example, had already an high income, okay, so I want to measure the effect of an increase in some policy on the income of individuals. If there was already an increase, an higher, there were individuals, so the treated group had already an higher income because of some characteristics. For example, they have some inherited wealth from the family, and this is W in this case. Then we need to clean for this difference. And we do that by basically, so these are the points that we have, okay? So this, and this. By using this difference in difference, it's like we actually generate a new point here, which is basically, as you can see, cleans for this difference in the intercepts. As I told you last time, there is also something which reminds us of what we did with the before and after change with panel data. So whenever we do that, this is the idea of the difference in difference. Then basically we are accounting for, we can write this estimator, which we call beta 1 DID, as the estimator for this coefficient where we regress delta y on the treatment variable. Okay, and this is something that we can estimate by OLS. So delta y is post-experiment, so y post-experiment minus y pre-experiment. And then this is an example. So just going back to one of the earliest applications, John Sean, this is an economist who was interested in understanding whether the cholera was transmitted by water or by air. And we have a district in London that had changed water source, and after the change, cholera deaths in that district decreased. Okay, so if this is the case, so we might be led to actually say that this change in the water was good. Okay, so actually the water that was before was the source of the infection. But there are other characteristics, other variables which may affect these transmission. So whether the cholera has been transmitted by water or air, and there might be also differences over time. So that's what we account for by using difference in difference estimate. So let's build. So we need to basically go back to the elements of the difference in difference, which are, we need a treatment group, we need a control group, we need two periods. Okay, and then we need a variable W, which is unobserved, and we assume that this is the timing variable. So in this case, which is the treatment group? This is the houses that changed the water source. Okay. Then we will find the control group. Okay. And to find the control group, we need to first think, so which is the variable which is unobserved, okay? And then I will find a control variable which will control for which will control for this W. So let's see this. But basically, the first type of evidence we will be induced to perform, to search for, is this before and after comparison. So before the change in the water source and after the change in the water source. And this is this conditional mean in population. Okay, so the conditional mean of the y variable when we are treated, and this is the post-experiment. So after the change in the water source, we are still in the case of the treated group when instead we are before the change. Okay. Then the key question is is this conditional mean the same? If this is the same, this means that actually the change in the water source doesn't affect the transmission of cholera, right? Okay. And then why are we concerned about just comparing the before and after conditional mean? Because the question is the observed outcome before the change a good prediction of the counterfactor after the change? So what does it mean? So we need to generate another group with similar characteristics to the treated group, where actually, which will account for variations, cross-sectional variations. So let's see what I mean. So we can actually use the before and after change, so before and after comparison, if nothing else changed at the same time as the treatment. Okay. So if no other changes happen between these two periods, these 2 years, then we can just compare actually these 2 periods and we will get the effect of the change in the water source because nothing else changed there, okay? But if maybe there are other variables which actually affected the outcome variable between the period 0 and period 1. So maybe this difference in the conditional mean doesn't come only from this policy, but maybe something else changed. That's why we need the control group, okay, to account for something that changed over time in these 2 periods. Okay, so the question is always the same, and then in this example we are concerned that actually there are other variables, so like the air, which could have been which could have explained this contamination, this source of infection. So we identified another variable which could have explained this phenomenon. This is the air, and given this we use a control areas. Okay, we need a control group, and these are all those areas where basically where this treatment has not been implemented, so there was not this change in the water source, and of course there was the same air. Okay, so this comparison to the control group, so the comparison to all the areas where there was not change in the water source, but there was also the same air, helps us to clean for these confounding factors. So we want to clean for all those factors which actually change over time, other than the change in the water, and we do the before and after, and then we compare treatment and control because we want to clean for actually other variables which could be instead different. Okay, so we want to hold the air constant. The air is the same over these 2 periods, over these 2 groups, and so by comparing cross groups, we hold this W constant. So then doing this, so by comparing what happens in the also in the control group. So what happened in the treatment group? So this was our first question. We do the same for the control group. So where x, the treatment, is equal to 0 before, after and before the change. And then this beta 1 is what happened before and after the change in the treatment group minus what happened before and after the change in the control group. Okay, and this entails 4 conditional expectation. Okay, 4 expected values that by estimating this model in delta y in changes of the outcome variable will be basically accounted for. Okay. So now you can, of course, look into this slide, but I want Francesco to come. And we will do a problem set on this, and I will help you with this. But basically, the idea is that we just need to be very careful with the data, because we have, as I told you, a time dimension before and after the treatment, 2 groups, and fixed factors. So that is the only thing that we need to be careful, but then for which we need to be careful, but then the estimation is by OLS. Okay, so nothing really difficult is there. So let's, and I will be there with you, so I will help you with the problem set, of course. This is on Monday. Then on Tuesday, there will be this PhD student online. He will present online, and then on Wednesday we will do a mock exam. So let me hold it.